بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, welcome to the third lecture on deep learning for language modeling. And today we will be talking about word embedding and vector representation in language modeling. So if you remember in the previous two lectures, the first lecture, we have introduced an overall history about deep learning and how we moved from simple perceptron into a transformer technology that now has transformed the whole language modeling research and even approaches. And in the second lecture, we talked about tokenization and its importance for language modeling, and in particular to learn about the morphological representation of languages. And today we are in the second step of language modeling processing, which is the embedding models and vector representations of the words or the subwords or the tokens. So first of all, we already introduced the fact that machine learning doesn't understand text or characters, they only understand numbers. So usually we're going to transform everything, every textual information into a vector. And I would like to make a refresher about vectors. I know that all of you have already seen vectors, but probably there is some kind of abstraction. Why do we represent word of vectors and how do we represent them, and what is the relation of the word semantic and linear algebra? Because everything is based on a very important concept related to the dot product about two vectors. So I would like to remind you these very beautiful findings from the linear algebra and how we can capture the semantic of words by representing them as vectors, and we use a nice foundation in linear algebra to measure the similarity between vectors, which is a very simple models or a simple theory, but the way how it is now applied in transformers in language modeling, it made a complete revolution. So of course, a vector in space, this is 2D vector representation, very simple. You have an x-axis, a y-axis, and you represent the vector as such. And then you will represent this vector either in Python using NumPy array usually, or in mathematics as just a vector with two values. This is something very foundational. And basically a vector will represent a coordinate in space. Okay, so we can see it as a geometric coordinate in space. In 2-dimensional it's 3, 4. It can be also in 3-dimensional, like we represent the GPS coordinates, altitude, longitude, and latitude. And of course, with contextual information and textual data that we converted, we will work onto much higher dimensions, can go up to several hundreds or even thousands. And there are different types of vector operations, so we can make the sum of vectors, the subtraction of vectors, we can multiply a vector by a scalar, all these different types of operations in linear algebra. And yeah, this is how we can do that in Python, very simple. Okay, and this is the sum of two vectors. What does it result? So if we have a vector w and the vector v, so this blue vector is actually the coordinate of the sum. Okay, v plus w, we're going to sum the x values and also the y values, and it will result in another vector with a different direction. Okay, so here every vector will have a magnitude and a direction and angle. So all of these, they would have very important meaning later on in NLP. This is why I am making refreshers. Okay, so why do we use vector in deep learning? We use them to represent images. Okay, we have already introduced this. So this is what an image looks like for a computer. Okay, so it's a 3-dimensional array or matrix that represent 3 different channels, red, green, and blue. And it's also used in NLP, and this is our interest. So when we represent a word, we can, as a vector, so it will have some kind of float numbers. So one thing is, okay, how should we represent this word using a vector? Now that's the question. So it turns out that we need to, words, they carry out some kind of semantics. And if we represent the words with random vectors, we're going to lose this semantic information. So I have introduced several concepts. Now, when we say semantics, what does it mean, semantic or two vectors? When we say a king could have another synonym, for example, it's close to a man, if we look at the gender. So there are some kind of similarity to some extent. Okay? Now, if we represent a man by a vector and the king by a vector, how can I capture that these two vectors are close to each other? This is the question that we try to answer now from mathematical perspective, because everything later on in machine learning or in deep learning will be just operation on these vectors. So we need to know how we can capture the meaning or the semantic or the similarity or how close this vector should be. Let's look at this example. This is just a factual example. I took some random values, just to introduce the concept of embedding vector. So embedding, it means converting a word or a text to an embedding vector. So we can take an apple. This is just a manual conversion, doesn't carry any sense. Okay, the most important thing is that embedding is to make a mapping between every word and its corresponding embedding vector. And then, we will have a mapping. Given a word, I apply a function, okay, it will return me an embedding vector. And so now, how we can calculate we want to calculate the similarity between two vectors. So let's look at one of the embedding libraries that is available. So this is now a real embedding libraries. It means it was trained on different words. And let's make an observation. So we're going to load it from SPACI, this, okay? And this embedding was trained on web information, but it has a small size. It was trained on a small corpus. And then just applying the embedding function, NLP, okay? So we can get the embedding vector, so I convert it to a document, and then I will access its vector. And this represents the representation, the embedding representation of Apple based on this embedding function. So this embedding function takes a word, converts it to what? To a vector. Okay, so this is just converting one word into a vector, and this is the idea of embedding. Now, we learned how to convert a word to a vector, and there are some kind of embedding library that does this. But what are the characteristics of these embedding libraries? Now, we ought to understand how these embedding libraries are capturing similarity. We need to understand the concept of dot product. You probably have already seen it before, but you need to realize how this is used in NLP to compare similarity between words. So mathematically speaking, the dot product of two vectors is calculated as a weighted sum. You have a vector W and a vector X, and then you will the dot product will be just a scalar, X multiplied by W. Dot product will be the scalar, which is the sum of the product of Xi and Wi. Very simple. So this is a simple equation, but it has a lot of meaning. Okay, this is mathematically speaking, this is how we can do in NumPy. In Python, we can do np.xw. It's going to return the same thing. And also, we can use the @ So this is equivalent in Python. And this is how we can do this mathematically. If you have X and W, X dot W is equal. So we take X and the transpose of Y, and then X1, Y1, X2, Y2, and X3, Y3. And this is going to give a scalar, -2, for example. Now, what does the dot product represent? Now, we understood mathematically how to calculate it. But this has a lot of meaning. This is fundamental, a fundamental concept that is used in NLP. let's look at the effect of a dot product. Now we have this vector in blue. It has coordinate 1, 1. And this vector in red, it has the coordinate -1 and 1. So forget about the equations. These two vectors are what? Are orthogonal. Okay? And their dot product is equal to 0. It means that they don't share, and they are orthogonality in linear algebra, it means they are completely different. Okay. So the angle here is 90 degrees. It makes the cosine is 0, and the dot product, dot product is related kind of the cosine, okay, of unit vectors. And let's take the other extreme case. Two vectors are identical, similar. Okay, I have a vector 1, 1 and another vector 1, 1. The dot product is 2. It's high now, positive and high. Let's make more observations. I have two vectors, 1, 1 and 0.5, 0.5. So they have exactly the same direction. So the relative angle between both is 0, but they have different magnitude. What is the dot product here? Is 1.0, so it's half of this one. So the magnitude will also play a role on the value of the dot product. But they have the same direction. So usually in NLP, when we do normalization, the effect of magnitude is not going to be significant. And what remains? Remains the angle. Now, if I take this one, 1.5 and 1, 1, this will give a dot product of 1.5. Now, there is a difference both in magnitude and also in terms of the angle. So when there is an angle between two vectors, this is where we have more dissimilarity. So similarity, it means when these angles are 0, we say that they are similar. They have the same direction. التوجه اعتبروه توجه الكلمة. Okay? If they have the same angle, it means that they have the same meaning. And if the angle increases and it becomes 90 degrees, it's basically 0. Okay. And now let's do another case, completely the opposite. It's not 0 here, but we're going to have a negative dot product. They are completely opposite. So there is different and opposite. Opposite is different, but it has another meaning. Okay? For example, now if I take it from language perspective, slow and fast. You cannot say that they are 0 relationship, but they have opposite relationship. Okay? So now you can see the magic of linear algebra. Through the vector representation, we are able to represent the semantic information between the vectors. Now, the question becomes now, if I need to do a vector representation of words, how should I make it such that I can maintain the semantic similarity between the words? Because now I have a tool in linear algebra that will allow me to measure this similarity, اللي هو الدوت product. صح ولا لا؟ فيبقى السؤال الآن, what are the techniques that we can use, سواء based على training or other things, that will allow me to make a vector representation of a vocabulary, of a corpus, in a way to be able to capture the semantic relationship between the words. We will introduce it. But now we know that there is a tool, the dot product, that will allow us to do that. Okay? And the whole objective of embedding is to transform a word into a vector, but I should not transform it in any way. It must have a meaning, a semantic. The vector must maintain and carry out the semantic of this word with respect to others. واضح الإشكال? And today we will see different techniques on how we can achieve the following. Now coming back. On this example, now we've took the core web MD, it's medium. The previous one was large. Now this is the medium one. And I make the dot product between apple and banana and apple and lion. And look here. This gives 911 and this gives 161. So this embedding is able to know that banana and apple are more similar than apple and lion, because here the dot product is smaller, and here it's positive and high.
It is higher. We are closer to the zero.
طبعا, yes. A high dot product, it means higher similarity. A low dot product, it means lower similarity.
Okay. We have from 0 to infinity?
Yes. Now I just give you something that was trained, and I wanted to illustrate that it is able to carry the information, the semantic information. In this lecture, I will show you how we can train models that can carry this information. And this is the concept of embedding. شوف الآن this code. Okay. I just convert these words using the embedding function and then calculate the dot product. That's nice. Now doing the same thing, but look, using the smaller model. Is it able to capture the relationship?
No.
Apple and banana, 39, apple and lion, 35. I would say yes, but less significant. Yeah. Okay, so we can observe now, we can make another observation. A larger model has the ability to make better differentiation. واضح ولا؟ لما عملنا الام دي هنا, the gap is larger because this was trained on much more words, much more context. So it was able to learn richer information. This one was trained also, but because the vocabulary is smaller, it has been able to capture some nuances, but still, not at the same extent of the bigger model. Okay. Now this does the job, but partially. Let me explain why. Because now we're going to consider the difference in the dot product. We'll consider two things: the angle and the magnitude. However, we want to focus more on the angle for the differentiation. And this is why we have another tool which is called the vector normalization, which is really very, very important. It's not only on this, but in the whole training of deep learning models, large language models, and so on. Because it's with vector normalization that we are able to stabilize the conversions of these models and don't have kind of vanishing gradients or exploding gradients during the training. So normalization is simple. We're going to divide every vector by its norm. So at the end, every vector will have a unit norm. If we do that for all vectors, the magnitude will not play any role into the differentiation between the words. Okay, because the magnitude of all vectors is 1. And this is one of the characteristics of embedding models. They will generate vectors with a norm equal to 1. Very simple. الآن الvector is composed of what? V1, V2, Vn. صح ولا؟ Numbers. I will divide by the norm, اللي هي by definition is the square root of the square of the sum. هذوما numbers, just make them and divide everyone by the norm. Does it make sense? So what happened? We have an original vector 3, 4 and a normalized vector. So the blue one is the normalized version of the red one. So what's the difference? They have the same direction. So the normalization doesn't change the angle. So it doesn't change the meaning. Now angle, it means meaning. Let's consider this. Okay? Similarity, it's related to the similarity. So now these are similar. But this one represents the normalized version of this one. The norm of this one is bigger than 1. So when I divide this vector by its norm, it will result in 0.6 and 0.8. And if you do the math, so we find that the norm of V is equal to 5. And then the normalized value is 3 divided by 5, so 0.6. And 4 divided by 5 is 0.8. So now the norm of this vector will be equal to 1. Clear or not clear?
The part was in the normalized vector is equal to 1.
Yeah.
What
What is the norm of this vector?
Okay, square root of
5.
yes.
And when you divide this vector by 5, what is the norm of the resulting vector? 5 divided by 5 is equal to 1. Okay, take your time, look at the equations. You know, it's basically here. We will divide every value by its norm. And you say, okay, why this is important? I will explain. Okay, there are different types of normalization. The previous one is called so this is what we've done now, L2 normalization, اللي هي based على Euclidean distance. So this is the Euclidean distance between 0 and the value of x. Okay, what is the distance between this point and this point? Yeah, it's the magnitude. It's basically, now if I take in two-dimensional space, is the coordinate of x, y square. هذا هو الأكليدين distance نعرفه الكل. Okay. هذه square plus هذه square, it gives me this one. شو اسمه البيثاغور theorem. Okay. So this is in multi-dimensional space. It's also called the Euclidean distance. When we divide the vector by this norm, we call it L2 normalization. Okay, yeah. This is its name. And it's based on the Euclidean distance. الماgnitude. نسميها magnitude, نسميها distance. Okay, you can call it different things. But at the end, it's going to result into a unit vector. This one is going also to result into unit vector, but its calculation is different. So here, this is L1 normalization, and it's based on the Manhattan distance. The Manhattan distance is not linear like this. It's going to be, okay, so yeah, take different steps. Okay, it will take different steps until it reaches the value. So it's another way of distance, and it's basically mathematically it's expressed as the sum of the absolute value of the coordinates. That's by definition. Okay, yeah, this is the Manhattan distance. I go to x, and then I go to y. Whatever it is, negative, positive, I will take the absolute value. So you can take the straight line. This is Euclidean distance. وإلا, this path, this is called the Manhattan distance, and this is its expression. If I divide by this value, I got the L2 normalization. If I divide by the Manhattan distance, we got the L1 normalization. These are just definitions, and they are mathematical expression. Okay, so we use normalization also in computer vision, because the values of the pixels are usually between 0 and 255. Okay, in order to have better and stabilized computational performance, we want values between 0 and 1. So one of the ways we can divide by the maximum value, that's some max Z max normalization, I think. Or we can divide by the Euclidean distance among all these values, and also it will result in a vector whose norm is going to be equal to 1. And this is the normalized grayscale. Okay, there is no difference. Look, visually, it will not change the patterns of the picture. So the normalization is not going to impact the patterns. You know, في باش تعمل feature extraction, the feature has to be maintained. Okay, I should not make any change. So normalization doesn't change any feature inside the raw data, but it actually leads to better representation. One of the reasons is to have better computing performance. Okay, لأنه مثلا لما تشتغل بأرقام أكبر من واحد, you do multiple multiplications. You know that all deep learning is about dot products, multiplication, and sum. So you can get to values very high, and the computation will be unstable. You can go to infinity, and you can crash your training. Now, in normalization in NLP, we do the same thing. Okay, so the vector norm for apple, banana, and lion, we find 43, 31 and 55. Okay, and we can do that using np.linearalgebra.norm. It's going to return these L2 normalization values. And then after that, we can represent the normalized vector. So this is the normalized vector for apple. And basically, the normalized vector is basically the vector divided by the norm. So we calculate the norm, we divide, and we divide the vector by each norm. We will result into another representation, which is the normalized representation of the word. So this is an embedding which is normalized. Now, no one asked me why we need to do that. احنا الآن قلنا الامبيدنج في الأخير it has the ability to know the semantic similarity, but still it's unstable. Let me show you. So a better representation of the dot product for semantic similarity between two vectors is to use the cosine similarity, which is basically a dot product, but divided by the norms of the vector. Okay, so this is the definition. You have two vectors, x and y. The cosine similarity, dot product on the top, and Euclidean distance in the denominator. And these are the two vectors, A and B. The cosine similarity is 0.96. Okay. So why it's better to use cosine similarity rather than the dot product? And basically here, it's the dot product of the normalized vectors. So this is normalized vector of x, and this one is the normalized vector of y. So the cosine similarity is the dot product of normalized vectors. واضح مش واضح؟ إذا مش واضح قولي لي مش واضح. ها؟ مش واضح. What is this quantity? X divided by its norm. It's what? فماش dot product. X divided by its norm. We call it what? Normalized vector of X. صح ولا لا؟ وهذا normalized vector of Y. وهذا من الاثنين dot product of what? Of normalized vectors. واضح؟ فالcosine similarity is the dot product of the normalized vectors. Okay. الآن تكلمنا كثير mathematical. خلينا نشوف الامبليكيشن. Now, when we calculate, this is a heat map that calculates the cosine similarity between every two words. الأحمر high similarity والأزرق low similarity. شوفوا منطقي جدا. طبعا كل كلمة متفقة مع نفسها. highest cosine similarity دائما cosine similarity maximum 1. والأبل والبناناس 466 makes sense. Fruit and apple 0.67 makes sense. So you can see now we have a concentration of red here and the concentration of red here, because here we have animals with animals and here fruit with fruit. But now if we check fruit with animals, it's blue. It's low cosine similarity. شفتوا الآن كيف الكوساين سيميلاريتي جميل جدا في إيجاد العلاقة المعنى علاقة المعنى ما بين الكلمات. dot product between two vectors. إيه شوفوا نعم نقارنوا two vectors فقط. تصير combination في الأخير dot product applied على two vectors تعمل اثنين وبعد اثنين آخرين. أوكي مفيد it's over two vectors. الآن bottom line observation, the cosine similarity is able to handle the semantic information on a normalized vector representation of words. اوكي وهذا كله مبدأ اللي يقوم عليه transformer from A to Z. مبدأ dot product. Okay, let's make the same example. Look now. We calculated the heat map for the cosine similarity of normalized embedding. لو نجرب الدوت برودكت على الامبيدنج نفسهم. This is without normalization. What is better to capture the semantics? What is better? أما أوضح العلاقات هنا ولا هنا؟ أما أوضح. The first corresponds to what? Cosine. معناها dot product of normalized. وهذا dot product of non-normalized. فصحيح في علاقات لكن even حتى الدياجونال يعني الرينج هذه okay doesn't give the same emphasis in the semantic relation لأنه here الآن الرينج 3000 لو نعمل other type of vectors يمكن تتغير ف it's not controllable dot product ف this is unstable okay this is not trusted. However this one is very consistent. Why? لأنه here the dot product it also includes the magnitude effect which doesn't actually impact the semantic. And this only cares about the angle. So when we build an embedding, we want to have larger angle between vectors of distant words, and almost zero angle to for vectors same word. لأنه الوان هذا it's cosine of zero. Cosine of zero is what? What? Cosine of 90 zero. هذاك علاش نسميها الكوساين similarity. يعني it's the cosine between two vectors. هذا من القيم it's the cosine between the vectors. والcosine this is what gives us the semantic information in a vector representation of words. ولا documents later on ولا sentences. هذه القاعدة اللي ينبني عليها كل الامبيدنج وفيما بعد الكونتكستوال embedding ولا large language models. Self attention it's inherently built over this concept اللي هو dot product ما بين طبعا ناخذ سنتنس مش نشوف العلاقات ما بين الكلمات في السنتنس هذا. كيف نشوف العلاقة؟ كيف نبني الامبيدنج اللي يعطينا العلاقة الصحيحة؟ بالاعتماد على الكوساين similarity between every two words موجودين داخل السنتنس. Of course, transformer GPT, this is the state of the art. Like today, we're going to start from the history, from where we started, how we calculated the embedding vectors of words, which we call word-to-vec initially. Okay. So you can see the impact of normalization is very clear. Okay. Now, just to conclude, we use cosine similarity. It means the dot product over normalized vectors, embedding vectors, to check whether two words are similar or are different. السؤال اللي يبقى باش نحاولوا نجاوبوا عليه today in this lecture, how we can build an embedding vector representation of a vocabulary or a corpus to maintain the semantic information. That's it. هذه إشكاليتنا اليوم. واضح ولا؟ That's it. اوكي فهذا الريفرشر لينير الجبرا مهم جدا باش نفهموا من بعد لما نقول فيكتور ريبريزنتيشن اوف وورد تبداش حاجه هكذا هلاميه تبدا حاجه واضحه في الذهن. اوكي والكوساين سيميلاريتي والسيميلاريتي كلها مبنيه على الاسس هذه. This is the ground. ومن بعد we're gonna build different approaches on that will actually be related to this concept. Okay, let's stop now and we continue after the prayer. بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, let's continue lecture 3. So I have already introduced the linear algebra concept and I hope that you have understood the relationship between the vector representation and the semantic between vectors. So the semantic between vectors is captured by the dot product, and not only the dot product of vectors but the dot product of the normalized vectors. So what do we expect now? we expect to build a vector representation of words or of a corpus such that the vectors of two words that are close in the meaning between each other will have a dot product or a cosine similarity the highest possible, equal to 1, or the closest to 1. That's the idea. Okay. So in this lecture, I will explain the fundamental concept of word embeddings and vector representation in natural language processing. And also I will compare and contrast different embedding models, including one-hot, which is the most simplistic approach, count-based, and prediction-based approaches. I will show some basic implementation of word embedding techniques, such as the TD, IDF, word-to-vec, and fast text, and GLOVE as well. And you will analyze the linguistic embedding challenges, morphologically rich languages like Arabic. So let me remind the language modeling pipeline, which starts from an input text and then tokenization. We completed this part. And now we are here in the text embedding, and we want to understand how we can make a conversion of a token or a word or a subword into these kind of vectors before feeding the input sentence into a transformer task, which is responsible for extracting the contextual relationship between the word in the corpus. So first, let's try to understand the meaning of an embedding. So what is an embedding in LLM? An embedding is a dense vector representation, okay, in a high dimensional space. It makes sense. So it means we will have a vector with high dimensions. For example, 1,000 or 10,000, depends on the context length we want to represent, that mathematically encode semantic relationship between linguistic entities. I think with the introduction that I have done, this should make some kind of sense to some extent. And the property of embeddings in LLM is first to reduce the dimension of the corpus instead of manipulating, transform categorical data into compact vector representation, and semantic similarity, position similar words closer in a vector space, as already introduced. Context awareness, that is even a much demanding requirement. It's not only the relation between two words, but within a context. Okay? Dynamically adjust based on surrounding linguistic context. And also transfer learning enable adaptation across various NLP tasks like sentiment analysis or translation. Okay, so this is an illustration. So dense vector representation means transforming a word into a vector that will capture semantic, context, position, and relation. And also we need to maintain the semantic relationship. It means we need to understand the relation between cat and animal, to which extent, the cat and dog, to which extent, the cat and computer, you know. This is like the cosine similarity between the different embedding or normalized embedding vectors. The context awareness, look at this example. When I say bank, what does it mean, a bank? So maybe the first thing is, this is with money, financial institution. But also a bank, if I put it close to a river, it will have another meaning, okay? So this is why sophisticated embedding models, they will consider not only the binary or mutual relationship between words, but within its context. هذا الشيء يعمل ChatGPT ولا large language models. They are able to capture the whole context meaning. We put all the context just as a whole into the input, okay, the whole input context. So bank in financial context could be encoded in this way and could be encoded in a different way. هذا contextual aware representation, we're not going to cover it today. We're going to start cover it since next lecture with recurrent neural network, which are more sophisticated techniques that are able to capture the relation within a whole sentence, okay? And LSTM, for example, for short long-term memory, to be able to embed the words that have different meanings in different contexts. But today, we're going to work with word embedding models, and this word bank will have the same embedding regardless of its context. Okay, because the embedding models, they have made an evolution Okay, they were only just vector representation with no semantic similarity, and then they moved to semantic similarity between words, and then they moved to the contextual semantic similarity, which comes with transformer-based approaches. Okay. So why do we need embedding models? Okay, we already talked about word similarity. Okay, we need to understand the synonym of different words. So traditionally, and this is what I'm going to introduce at the beginning, the words were represented as one hot encoding. Imagine that I have a vocabulary of 3. I can represent this word as 100, this word as 010, and this word as 001. That's a possible representation. You know, at the end, it's an embedding. I map this word to this vector. But what is the problem of this embedding model? This embedding model, you know, see these words. They are all related, صح ولا? Now, if I apply cosine similarity on this, these vectors are orthogonal. So all the cosine similarity will be equal to 0. So this is one of the representation, but it doesn't carry semantics. Okay? And we need to also have contextual meaning with more advanced embedding models. We talked about this, the synonyms and antonyms, and also the sentence structure, sentence similarity. You know, we go beyond word similarity to sentence similarity. Now, the cat sleep on the mat. And look at this sentence, a kitten is napping on the rug. It's basically the same meaning, but completely different words. And this makes more challenge. Okay, so we have word similarity and we have sentence similarity. But of course, this with contextual type of embedding models, it will be possible to capture this relationship. Okay, also the Arabic language, it's a rich morphological featured language. We can have the embedding similar to involving nested phrases with larger structure. So look at these phrases. You can have a simple sentence, قرأ الطالب كتابا. We can have an additional sentence, قرأ الطالب الكتاب الذي استعاره من المكتبة. وأظن أن الطالب قرأ الكتاب الذي استعاره من المكتبة. So here we have different type of sentences, but they are semantically related. So we need to have embedding models in order to be able to have a correct representation of the language morphological structure and also the semantic information that is carried out with the different words. And one of the basic applications that we currently use is to retrieve documents. Okay, for example, I would like to search for information into a large amount of PDF files. So usually these PDF files, they can be transformed into a vector representation. And then when you look for a particular type of information, we will do cosine similarity between your query and all these documents. And then we will try to provide the documents that have the highest likelihood that your query will find an answer into that document. Okay, and this is part of the retrieval augmented generation in large language models. Now the current chatbot, they rely on this technology. لأنه relying on querying the large language model, sometimes it doesn't have the sufficient information to provide you a correct answer. Now let's take a question. You make a chatbot for Al Faisal University to respond to any query here. If you ask ChatGPT, DeepSeek, or whatever language model, it will not provide you the very specific information of the university. صح ولا؟ So one approach to do is, instead of asking the LLM, I'm going to ask the documents first. Okay, because I will try to retrieve these documents. So you will make a query. What is the admission requirement in software engineering? And of course, now if we want to do this manually, you need to open the PDF that is most likely to have, for example, admission policy. And you need to read several pages until finding the location where it talks about the admission process. Now we can do this using semantic similarity. What I do, we're going to divide the policies into chunks, and each chunk will have certain logical information. For example, a chunk on admission policy, another chunk on dropping a course, another chunk about registering to a course. And then based on the query, using this vectorized representation, we will use still dot products, cosine similarity, to find the documents that are mostly related to your query. Of course, in order to have an excellent retrieval, we need to train these models to be able to understand not the word level semantics but the sentence level semantics. هذا هو التشالنج، واكبر تحدي الان هو ايجاد الدوكيومنتس. يعني الشات بوتس الان امورها يمكن solved at almost 100%. The most critical problem is not the LLM, because we don't rely on the LLM for information or knowledge. We rely on the LLM just for generation, but we rely on the retrieval in order to find the most relevant document to the query. This is the challenge. So basically, embedding is an important milestone in any kind of language modeling task. Okay, it's really crucial. وكل جزء ترى معناها it has its importance. يعني التوكنايزيشن تكلمنا عليه الاسبوع الماضي. If we don't do tokenization well, we will end up by bad embedding and bad language modeling. فكل شيء مرتبط ببعض. لأنه اللغة صعبة. It's something very dynamic. فنريد احنا، ولذلك ما نستطيع نحصر اللغة في قوالب، ولا الناس كانت تعمل if then statements and then they can find a solution to, but it's much more complex that we need just to find the best patterns possible for every kind of language. Okay, and tokenization and embedding are complementary parts. Okay, so tokenization is mostly about the morphological structure, and the embedding is mostly about the semantic structure of the language. Okay, so the first approach, which is very simplistic, as I already talked about, we take a corpus of words, and the simple way to represent word as a vector is just to assign one hot encoding representation. And what hot encoding, it means we're going to have a vector of all zeros, only one part. For example, if I have a vocabulary of 5 words only, imagine that this is my whole corpus. So just a vector representation of 5 elements is sufficient to have different vectors for each word. Now, this one will have 1, 0, 0, 0, 0. This one will have 0 here and 1 here. So every time I'm going to change the place of 1 to make a differentiation between both. That's fine, it gives a diversity. I'm able to map every word to a vector representation, so later on I can feed it to a transformer or feed it to a deep learning model, machine learning model. And this is one of the techniques used in multi-class classification. Okay, when you have a softmax function that will estimate what will be the category, so we can represent the category using one hot encoding like this, and we call this encoding. We don't call it embedding. What's the difference between encoding and embedding?
I think encoding means just all can be 0 ones.
Mm-hmm.
While embedding is
No, not really. مهم التفريق. الآن حتى في الترانسفورمر we have positional encoding, we have positional embedding. The difference is that encoding is learnable, embedding is learnable, and encoding is not learnable. شوف الآن, this encoding is not learnable, it's just an assignment. And encoding is something that we are going to learn using a machine learning model, neural network, with back propagation, optimization to get the values. But this is the most, and this is why we call this one hot encoding. Look, I didn't say embedding here. Okay, because it's not learnable. And later on, we will have Word2Vec. It's an embedding model because we're going to use a neural network to train and get the embedding, which will be values between 0 and 1s, okay, to represent in the continuous space. This is a discrete space, and in the embedding, it will be a continuous space.
Doctor, which one is learnable?
The embedding. Embedding is learnable. And look at this, is not learnable, so it's encoding. Okay, وذلك our paper for transformer can يستعملوا positional encoding. They have a sign function that actually will provide the position of every word in the sentence. And then they change this to embedding. The position is also learnable with the word embedding as well. So, as we already discussed, the one-hot encoding, it has many limitations. Of course, it's simple. We can represent every word with just a vector of 0 and 1. but it doesn't bring any semantic relation. Okay, if I represent happy, and I don't know another word, Saeed or Farhan. So these two vectors, any vectors in the corpus are orthogonal, so the cosine similarity is always 0 consistently. And it has also high dimensionality because this will depend on the number of words in the vocabulary. Of course, 10,000 is not even big. If we take the whole vocabulary in Arabic or in English, it's going to be even hundreds of thousands. So it's really difficult to manage the dimensionality of words. It's not context sensitive. It doesn't have even relation, not even aware about the context. And it doesn't know anything about the morphology. So this is kind of the worst way to represent a language model. Okay. The only advantage is that it's simple and it just maps every word to a vector representation. That's what it does. So this is very foundational and fundamental. And the solution now is we move from encoding to embedding. We learn the embedding from our whole corpus. And to have a dense vector, so this is called a sparse vector representation. It's like discrete, okay? And this is dense because it is in the continuous space, so it will have a certain dimension, okay? Could be 300, 100, or now, we have a couple of thousands of embedding vector representations. And of course, the dimension is related to the size of vocabulary, okay? If you have a large vocabulary size, you need to have higher dimensions. So the embedding, they are able to find the semantic similarity between words, the morphological awareness, capture the relationship between word forms, and also they can even learn the context, within the context, of course, depending on the algorithm. Okay. So what are the different embedding model categories? There are 4. And there are subdivisions, but I wanted just to aggregate them into 4. The count-based, we're going to map every word to number of occurrences or its frequency in the document. And this is very simplistic, but still it's helpful to make kind of a vector representation of a word and help also to solve some basic search functions. Okay, I will search the word that is more repeated into a certain document. So this is based on frequency-based models, very simplistic, but it can solve some problems. Prediction-based, and this is the main focus of today's lecture, it's learnable embedding models. So we will go and learn embedding by training small neural networks. It's basically one hidden layer of neural networks which will represent the feature representation or the embedding model representation of these different words. Okay, neural network on prediction tasks, approaches like word2vec, Clove, and fast text. These are what we'll present. Other categories, contextual based and transformer based. This will be the subject of the next lectures. And here it will generate dynamic vector representation that adapt to the specific textual context. So it's not like here, it's only the relation between the different words, but here it will have better understanding of the whole context. Okay, and demonstrate embedding can change based on the surrounding words. So in this case, every word will have a single embedding. But here, a word can have different embedding. مثل مثال بتاع البنك على حسب الكونتكست هل هو بنك أم مقعد. Okay, it can have different type of meaning. And transformer based, this is like the revolution. It's not only an embedding model, but it's a whole language model. And embedding is trained along with the whole language model. So we're not going to provide a standalone embedding for a transformer, but the transformer is going to learn the embedding of the words and is going to learn all the relationships between these different words. And it will encode not words, it will encode tokens that comes from the tokenization part, considering their entire sequence context. And this is why we have long context length in transformer-based language modeling. And it starts with BERT, GPT, T5, MT5, all of these we're going to go through them, inshallah, during this course. So this is the summary, just to give you the landscape about these different categories. So the first one we're going to start with is the count-based TF-IDF, and is going to look at the frequency of every word into each document. Imagine that I have two documents, and in this document I will have the word cat appears 80%, and the word dog appears only 1%. So if I make my query cat, so it's most likely I'm going to find a response into document number 1 and not document number 2. Okay, so every word is going to be assigned into a probability inside a certain document. So it will capture the word importance in documents, but the limitation, it doesn't have any clue about the relationship and the semantic relation between words. Okay, هذا فقط يركز على الكلمة بدون أي علاقة مع كلمات أخرى. It doesn't bring any semantic meaning. Okay, and this is not really a true embedded model. It's a way on how to transform words into like frequency based on documents. And it's a very popular algorithm, this one, especially used in search. الآن لما تبحث على جوجل غالبا مش يستعمل TF-IDF، يبحث على الكلمات، أقرب كلمات للكويري اللي عندك. طبعا الآن أصبح فيه semantic search اللي هو أحسن. The second approach that we are going to cover, prediction based. One of the most famous approaches is the word to vec. It means converting a word to a vector. And here, the focus in word to vec will be on the relationship between every pair of words. Okay? So capture semantic relationship and analogies. It's efficient, and usually it is low dimensional vector. But it's not going to have any information about the word in its context. فلذلك كل كلمة will be represented by one vector regardless of its context. لأنه التريننج مش يصير على العلاقة بين الكلمات. Okay, it will learn the relationship between every two words. Of course, the prediction-based model, there are other techniques that have global information, مثل الGLOF, okay, which is another approach that we are going to present today in the prediction-based, which will take the value before and the value after, okay, to provide the mapping or the embedding for the particular word. And this will result into several possible embedding models for the same word if it changes the meaning from one sentence to another. The most sophisticated techniques is the contextualized versions, like different vectors for different contexts, and the transformer based. مثلا الBERT was trained to find the missing word within a sentence. Okay, it will take the whole context and then will predict what will be this word based on the whole context sentence. So this use deep language understanding, deep language modeling, and state-of-the-art performance on NLP tasks. For embedding model, when we build it right, we can later on use it for downstream tasks, مثل sentiment analysis. Okay, we want to know the sentiment of a text, whether it is positive or negative. إذا العلاقات ما بين الكلمات مش واضحة, we cannot train a model to perform this type of downstream tasks. Let's get started by the frequency-based embedding models. Okay, so we talked about this. Now, what is the intuition behind the count-based embedding models? Is we need a numerical representation that reflect the word importance in each document. Okay, and we will use statistics of word occurrences and co-occurrences in a corpus to derive the vector representation. And TF-IDF is composed of two parts. The first one is the term frequency, and the second part is the inverse document frequency. And I'm going to explain. Okay, so the term frequency, it means how often a word appears in a document. باش نحسب عدد الكلمات الكل. والله عندي 10 كلمات، كلمة كات تكررت مرتين، فعندي 20%. So this gives me the importance of this word into a document. Okay, and the inverse document frequency is how unique the word is across documents. يعني لو فرضنا كلمة تكررت كثير من المرات، مثلا ناخذ the word the، يمكن تلقاها متكرر 20 مرة في كل دوكيمنت، لأنه نستعمله للتعريف، فيفقد القيمة. الكلمات اللي ما تتكررش بكثرة very unique in a specific context هي اللي تميز الدوكيمنت. فنشوف الفريكونسي كم اتكررت how unique it's across the document. وبناء على ذلك we will make the product of both. هذا يعطينا الميتيوال importance. اوكي يعني الكلمة هذه تميز الدوكيمنت هذا. إذا تكرارها معناها كثير how unique the word if it is not unique so in this case it will lose, okay, because we take the inverse, okay, the inverse of the frequency. And let's see the formula here. So as I introduced, the term frequency of word W in D, and the inverse document is calculated by the log of n, which is the number of documents, divided by DFW, the number of documents containing the word W. حاولوا نفهموها الآن. TF واضحة. Counting of frequency. Okay, let me check. I think I'm going to. I think I have. Yeah, I will explain. Just a moment. خلينا نفهم high level context. And the algorithm is actually to build the vocabulary of all unique words in the corpus, and then compute the term frequency of each word, and then compute the IDF for each word, and then calculate the product, and finally construct the TF-IDF matrix. Let's take it step by step. So the first one is to build a corpus. I have two documents. Document 1, the cat sat on the mat, and document 2, the dog played in the park. I know I changed this, because I made sentences with multiple words in the document. Look now, the cat sat on the mat, and the cat likes to play with the mat. Here, the dog ran in the park, the dog plays with the cat. Look, cat now appears in two documents. It appears multiple times here, the mat appears multiple times here. So we can make observation, dog appears multiple times, park appears only one time. So now I build a corpus. I'm going to take only the unique values. So the second is to compute the term frequency, which is the number of words W appears in the document D divided by the total number of words. Now, how many words I have here? In this example, I have cat, dog, park, and mat. I have 6 words. We consider them. So if we consider 6 words, the cat is repeated only one time here. So 0.167, and mat same thing. And I think I changed this one, but it gave me the old example. Anyway, let's just apply to this example. And the word cat in document 1 will have an importance of 0.167, which is the number of occurrences divided by the total number of words. Here I have 1, 2, 3, 4, 5, 6, yes. And the second one, we have also 6, so the number of words. Right? And this gives the following term frequency in each document. واضح هذا؟
طب دكتور الحين الامبورتنس الوورد على حسب التكرار، يعني كل ما تكرر كل ما قل الامبورتنس.
هذا باش يجي من بعد. الآن احنا نشوفه في التكرار. هذا تكرار الآن. statistical. Okay. Dog في document 1 is 0. ما تكررش. So this is just the probability of occurrence. Okay. Now we calculate the IDF. Total number of documents. كم عندي من documents؟ 2. I have 2 documents. Number of documents containing the word W. Okay. For all unique words, we will have the following. Okay. بالنسبة للlog 2, number of documents containing the word W. So we have 2 divided by 1. This is the IDF because because every word is going to be unique in each document. So here we have 1. And this is going to give 0.301 for all this. Clear? Okay. So this is the IDF. Of course, this is like a simple example because every word is repeated only once, but I have another one. It's going to come in just afterwards. You know what I did? I changed this one. It's a bit confusing because I made an example with this sentence, but I didn't change it in these two slides, but I'm going to update it, inshallah. Now, going back to the first example, and unfortunately I didn't make, so here, if I consider this example, here, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. The values are going to be different, which is in this slide. I'm going to make homogeneous later on, but just I missed this. Okay, so look now. If we consider the first example that I've mentioned, now cat will have a TF-IDF 0. Why? Because this IDF value will be here 0, because the word, look, the word cat, it is in both documents and it appears in all documents. It repeats and it repeats in all documents. فكانوا يعتبروا شيء غير مهم. طبعا لأنه عندي 2 documents only. مثل هذه just to element الwords مثل ال A, the اللي هم المعرفات. مش لما تبحث أنت على كلمة معينة طبعا مش يكونوا موجودين في كل الدوكيومنتس ف it will not make any differentiation. فشوف الآن لما استعملنا الورد كات في أكثر من دوكيومنت في المثال هذا اعتبره غير مهم لأنه تكرر. أوكي ففقد التركيز. طبعا لو كان عندي 100 دوكيومنت وطلع في 2 documents it will be changing because أنا my whole number of documents only 2 and it appears in all documents. If it appears in all documents is going to lose value. هذه هي الفكرة. وهذا لو ناخذ الورد ذي مثلا the word A المعرفات الأون 2 هذوما خلاص they will lose importance. فتصبح تركز فقط على الكلمات المفتاحية الكي ووردز في البحث. هذاك علاش في البحث يساعد على بحث الدوكيومنتس اللي فيهم كلمات مفتاحية معينة. It's only focused on giving importance to the keywords into the corpus. واضح؟ والكي وورد ايش تعريفه؟ هي الكلمات اللي تكون يونيك متكررة في دوكيومنتس. فهذاك علاش نعملوا الكومبينيشن اوف بوث. Make sense? Okay. So dog has the highest TF-IDF. خلينا نشوف الدوج الآن. 0.06. لماذا؟ تكرر في دوكيمنت واحد فأصبح هو معرف للدوكيمنت هذا. لو الآن نبحث I am searching for a dog ما هوش باش يضيع. Okay, it will have more focus on the second document because it has a high TF-IDF. So we're going to build a matrix of importance of every word with respect to its occurrence in the document. واضحة الفكرة الآن؟ TF-IDF. And this is a Python script on how you can implement it. It's very simple. So first of all, we compute TF. We count the number of words in the document divided by the length of the document. You can compute the IDF. This is how we do it. The length of the document, the docs, number of docs with number of docs that contain the word, and finally we do the log. We return the log. And the TF-IDF is basically the product of both. So the limitation of TF-IDF, it doesn't carry any semantic. It's high dimension. It's a sparse vector with many zeros. كثير من الأشياء باش تكون zeros. تخيل كل ما هو مثلا on at تكون zeros أغلبيتها, and same vector regardless of the usage. And this is not really considered as an embedding model, but it's just a way to help searching some relevant documents based on keywords. But it's a popular algorithm, especially now in retrieval. We use it in text similarity, we use it for retrieval, we use it for feature representation, and word. It's a precursor of the word embedding, which is the word2vec. These are just additional implementations on TF-IDF, and it's so for example here this is an implementation. I didn't show here the corpus, but let me show you just the code. This Google Colab. Show you an example. Okay, look at this example. So basically these are the same functions that I have introduced. Compute TF, okay, the number of words, the total number of words, and then we divide it. We compute the IDF, and this will return the compute TF IDF for the whole vocabulary, which result in the matrix TF IDF scores. So this will result in a matrix. And then this is an example that shows how we can use TF IDF to search certain documents based on keywords. This is my query. It's word embedding, and I have several documents. The first one, word embeddings are used to represent text in vector space. And here transformers have revolutionized natural language processing. BERT and GPT state of the art of NLP models. TF-IDF is a technique, and different words. So now we're going to apply the search document here. We have a query, we have multiple documents, and the search will be using the query, the TF-IDF matrix to find out the most likely document. Okay, so let me just execute this again, and look now, it will return the 5 documents with different scores. Look at this document, 0.18, and it returned the first document because it considers that it is more related to the query. Now, if I change the query, this lecture introduces word2vec and TF-IDF. Embeddings. Models. Look now, it returns models. Word2vec. This is the first one. Look, it has Word2vec, it has embedding. Okay, and then it returns BERT and GPT to represent NLP models. Word embedding are used to represent, and here it gives the likelihood of, or the score for every sentence. Okay, because there is model here, I was able to get it. And look here, I made embedding, so it detected this one and didn't detect this one. Let me try embeddings, because now embedding and embeddings are considered 2 different words. Okay, it doesn't have, now it made this one before. So it's based on frequency, on word counting, and it doesn't have any clue about the contextual meaning or the semantic similarity between the different words. Now, كان نستعمل vector store representation, الembedding والembeddings will have a similar meaning. So it's able to give a better search performance as compared to this one. لكن الآن في practical side we actually use a combination of TF IDF and semantic vector search to maximize the likelihood of documents that are relevant to the query. لأن كل واحدة عندها pros and cons. فمثلا لما تبحث في الفيكتور ستور خاصة when the document is very large, the similarity will be less emphasized. شوفوا الآن مثلا الفيكتورز هذا لو فقط ناخذ embedding models. ركزوا الآن على قوة السكور. في شيء عندنا شيء مثلا word، خلينا نكتب word embedding. شوف السكور الآن 0.18. لو نزيد كلام ثاني are powerful. سكور يضعف. فتخيل you have sentence similarity, okay, you'll have more pain to map a query with 5 to 10 words إلى document فيه 500 words ولا 10,000 words. Okay. One of the challenges that we have in retrieval is also the size of the documents and the size of the query. لكن الآن with the sophistication of embedding models, it's still able to find relevant documents. لكن in some context مثلا كنا بعض الأحيان نعملوا chat bots مثلا في الحديث ولا في القرآن, and you find that the combination of both can maximize الretrieval لأنه sometimes لما يكون النصوص طويلة جدا semantic similarity تكون نوعا ما ضعيفة لأنك you bring the right model. تسأل مثلا على مسألة شرعية وتحب تجيب أحاديث, مش بالضرورة السؤال عنده علاقة مباشرة بالحديث ولا مثلا بطريقة الاستشهاد. فمثلا making combination of semantic similarity with TF IDF أنه يأخذ مثلا سألت على الزكاة يمكن يبحث في نصوص الحديث كل فيها زكاة وليجيب على الأقل some of this. Okay. In practical settings we can use a combination of TF IDF, and this is why I presented, with semantic similarity to maximize the chance of relevance between the query and the document to search. Okay, this is very fundamental in retrieval augmented generation, because retrieval augmented generation, the query is your prompt and the documents are the supporting documents or evidence that might contain answers to your prompt. Then we're going to send the query and the document to the large language model to have the question and possible answers, and then it will draft the final answer, okay, using its reasoning capability. ولو تلاحظوا الآن التوجه في large language models بسميهم large reasoning models. We don't really rely too much on their knowledge, but we want to rely more on their reasoning capabilities باستخدام a chain of thoughts or other type of advanced prompts. So I wanted to go just a little bit broader to put all these technologies into the broader context, the target that we want to achieve by the end of this course. Okay, so okay. So the second type of models, besides the frequency-based, is the prediction-based embedding. And here, as already mentioned, we're going to learn the word representation. Okay, this is different from encoding. We're going to learn the word representation. And the core idea is to learn the word representation by predicting words based on their context. The advantage over the count-based method, we have dense vectors, we don't have zeros. Okay, we have semantic meaning. we can have better generalization of these vectors, and also word analogy supports arithmetic-like operations. مثلا man plus or king plus woman equal to queen. Okay, these vectors usually they can be summed up, and they can give you another vector with some reasonable meaning. Okay, this is what we call the word analogies, supports arithmetic-like operations. التريننج ابروتش الان I give you the landscape بعدين ندخل في التفاصيل مثل ما تعودنا. So these approaches are part of the word to vect. The word to vect it only captures the semantic similarity between words بدون context. وفي طريقتين. الطريقة الأولى اللي هي skip gram model اللي if I have a word predict the context word from the target. This is my target, and then I try to predict the context word. The CBAO approach, bag of word, continuous bag of word, it predicts the target word from the context. And I will show you the details later on. لأن في الأخير it's a neural network that's gonna be learnable to find these relationships. And the training process is to start with random word vectors that doesn't have any kind of semantic similarity, predict the word based on the context, update vectors to minimize prediction error, and repeat until conversion. And this basically use a one-layer neural network architecture. So yeah, all of this ecosystem is part of the word-to-vect architecture. We have the skip gram model and the CBAO model. This one, it takes an input, a word, and will try to predict a context, the context word. هذا بالعكس. إذا نعطيه context, the ruled kingdom. Okay, and actually the king ruled the kingdom. Okay, so this is how we can try to identify the semantic relationship based on the corpus that we'll be using in the training. And at the end, we're going to have vectors like this, which will carry semantic information. And we can have, for example, king minus man plus woman approximately equal to the queen vector. Okay, so here there is a gender feature, there is a role feature, and the word-to-vect is trying to understand the different type of features. Now I say gender, role, and so on, but in practice it's more complicated because we're going to have a huge number of words, and this is what we call the latent space. It's going to learn some features in the latent space, and this is kind of pattern recognition based on the corpus that will be provided as input. So now we are here. Okay, let me just move forward. I already presented all of this. Yes, now this is the intuition between word-to-vec. So you can think about, imagine that you have a corpus like this, man, woman, king, queen, apple, and orange. The intuition behind is that when we have, if we consider this is our latent space or our features, of course, in reality, we don't know what are these features, but this is just to make a representation. And here, we're going to assign different values. For example, the gender here, if I consider 1 is for woman and -1 for men, for the gender as a feature. So coming to the king, okay, so the king will have a value -0.95. Okay, it's proportional to this one because this represent like a role in a royal role here. And the queen will have a positive value with respect to the assignment that we've done over here. And apple and orange, will be kind of 0. So this feature doesn't apply, okay, to apple and orange. هذه الفكرة. This is the intuition. This is what the network will try to learn. We'll try to learn features in the latent space of these features, of these patterns. Now, if we consider a role of the royal role of king and queen, we can say 93 and 0.95. For men and women, we don't have really, it's not necessarily that royal, okay, is related to man and woman, but it's mostly related to king and queen, and of course here we will have almost also a 0 relationship. about the age. So here the age, a man and woman can have different ages, so the correlation is small. But for the king and queen, you know, it's likely they will have high ages, so it will have more correlation between queen and king. You know, you cannot have queen and king 5 years old. Probably it can happen, but you know, it's less likely to happen. So it's, you know, you can think about these numbers that we try to infer in the word-to-vec embedding as kind of relationship between words and their possible features. Okay, and apple and orange. Now, if we consider food here, we're going to have small relationship between these words and strong for apple and orange. And of course, these values are going to be learnable, and this is why we call it an embedding. But the idea is that we try to learn some possible features based on the different words that we get. So word embedding is mapping a word to high-dimensional vectors. This is going to be high-dimensional vector. This is just 4 dimensions, 4 possible features. But when you increase the number of dimensions, you may learn more features. Okay. And similar words will have closure representation. So this is how we're going to train our neural network model, is to learn closure representation for similar words and capture semantic and syntactic relationship as well. Let me check. Yeah, here. The gender dimension, the royal dimension, and the food dimension. Okay, we already explained this relationship between all of them. And this can be represented in space. We have also the Tesny representation. I want just to make something simple. If we assume that we have 3-dimensional representation, we're going to have points that are clustered. Maybe I will have queen and king just clustered to each other, and orange will be very far out of this cluster, and so on. So we're going to have a distribution in space. We will have a distance between the vectors that have very far representation. And the distance, what does it mean? Look, now if I consider this vector from here and this vector from here, they have small angle. كل عنده علاقة بماذا؟ بالcosine similarity. Okay, so when 2 points are close to each other, the angle is very small. Now if I consider this one and this one, it's wide angle. And this is why we can have negative relationship here, because they are opposite. And this one, maybe it's 90 degrees. So we can have 0 relationship between this point and this point. So it's basically point in space. But now I represent it in 2D, in 3D. Of course, in 100D I cannot make a visual representation, but it's basically the same concept. It's the dot product is the angle between the vectors that is going to decide about the relationship of these different words. Okay, so the word-to-vec in 3D space, these are just additional representations about how we can cluster these words. Okay, skip gram in word-to-vec. Let's have break, okay? You can digest this and then we can come back to it, inshallah. Any question? Does it make sense? شكون عنده صعوبات في الفهم؟ Yes. نو لسه ما دخلنا. الآن احنا نشوفوا ريليشن شيب ما بين كلمات. الكونتكست هذا نبدأه في الاستيام ومن بعدين في الترانسفورمر. فالورد امبيدنج الآن طبعا مش نتكلم على كونتكست لكن على نطاق ضيق اللي هو الكلمة اللي قبل والكلمة اللي من بعد حتى نربطها بسياق أوسع. لكن ستيل اتس ليميتد، يعني ما عندوش سياق كبير جدا. هو شنو يقول الترانسفورمر؟ يدخل لك جمل طويلة جدا وشوف السياقات الكل الممكنة. This is the ultimate case. لكن الآن طبعا هذا سنة 2013 يعني it's almost 10 years or 12 years ago أن بدأوا يلقوا علاقة بين الكلمات، يعني representation اللي تجد لك العلاقة بين الكلمات. It was a breakthrough at that time and it has opened up the horizon for many downstream NLP tasks مثل sentiment analysis بعدين text summarization كل هذه الأشياء. all what we are doing now is to find an embedding model that can capture the semantic relationship between every 2 words بدون سياقات. هذا بالنسبة للword to vec. وفي طريقتين، عن طريق الان سكيب جرام اوكي انجرام او سكيب انجرام اللي هو من كلمه يعمل بريدكشن الكونتكست، والا سي باو من كونتكست يعمل بريدكشن الكلمه. اوكي that's it. Any other question? هذا this is one of the possible semantic relationship. لكن semantic relationship بدون context. فالتطبيقات المتقدمة يكون ضعيف. لو نطبقه على sentence level ما يعطينا نتائج جيدة. يعطينا to some extent. لكن not to a very big extent. اوكي. يعني دائما مثل ما قلت يعني أصعب شيء أنك you find the best relevance. فكل ال embedding models وال contextual representation والأشياء دي الكل to be able to find the best أول حاجة language modeling to generate ولا حتى to retrieve a relationship between two different type of sentences or documents.